So we're going to make a start. So we're going to talk about advanced verification techniques for DO254. And here's the agenda for the evening. Okay? So we're broadcasting as well, so every now and again I have to check the broadcaster is working. So thank you for coming. I hope you find this useful. I hope you find it interesting. We're going to have some lunch afterwards. I think the talk will maybe an hour, hour and a quarter, and then we can go for some dinner and maybe talk, discuss some of the techniques we were talking about. Just before we start, how many in the people in the audience use advanced verification techniques? So advanced verification techniques may be formal verification or constrained random. Okay, so we have one. Okay, two maybe. And how many people work in avionics on DO254? Okay, so the other people are here for what reason? So you guys, some of you working in DO254 or not at the moment? You're working in DO254? Okay, okay. So this is going to be on the agenda here. We're going to talk a lot about advanced verification techniques and why people are starting to use them more and more, and why they're becoming more and more important in the way we do our verification. And then we're going to talk about how they can fit into a compliance arena, specifically on DO254. We work in medical arena, we work in the automotive arena, as well as in the avionics arena. And the compliance for all of those are quite similar. So it's not as if, you know, ISO 26262 for automotive is very different to DO254 for avionics. There's a lot of similarity. So we'll talk about compliance in general as well as 254 in particular. And then how do we combine advanced verification techniques with compliance? How do we use these advanced verification techniques within a compliance environment, which is the key challenge for us. Okay. So just to check, Sean, you can hear at the back, okay? It's quite noisy here, but you can hear. Okay. Okay. So this is me. My name is Mike Bartley. I'm not from India, from the UK, and I studied. I went to university a long time ago, back in the 1980s, when I did my PhD in logic. And following the PhD in logic, I worked in software, test and hardware verification for 25 years. A lot of this was doing formal verification. So these first two here is in software. And in software, they also use formal verification techniques, mostly VDM and Z. So they're using VDM and Z for development of software for Civil Aviation Authority in the UK. So it's an avionics project. And then these two are ASIC companies where we're doing a lot of hardware verification, and a lot of these techniques and practices which we talk about tonight come from an ASIC environment rather than an FPGA environment. So most avionics companies are working within FPGA rather than ASIC. But ASIC verification techniques are a long way ahead of FPGA verification techniques. So most of these advanced techniques have been deployed in avionics, in ASIC for a very long time. So they're very mature techniques that just haven't really impacted avionics yet. And one of the reasons is how do you get compliance as well as those advanced verification techniques. I also work for some startups, and we started T&VS back in 2008, and we have offices around the world now. And so we undertake avionics projects both in China, India, and the UK mostly, but also compliance projects around the world, and so we have offices around the world. Okay. Okay. So this gives you some idea of our background. As you can see, a lot of these here are ASIC companies. As I said, ASIC companies have been using advanced verification techniques for a very long time. They don't do that for any compliance reason. They do it purely for commercial reasons. Okay? And the reason they use advanced verification techniques is because a bug in any of their chips is so expensive. Okay, so if you're doing, how many people here work in ASIC? Okay, so, and how many people work in FPGA? So most people are FPGA. Yeah. So So we work with both types of companies, and ASICs tend to do more verification because the penalty, the cost, the pain of a bug is so much higher in ASIC than it is in FPGA. Okay? So the consequences of a bug on ASIC are normally not just the production run. So with the current technology, process technology, the production run may be $3 or $4 million to produce a chip. So if that's got bugs in that chip, that's $3 or $4 million effectively down the drain. You've lost $3 or $4 million. But more importantly, you've lost 3 months. And a lot of people see the 3 months as more important than the $3 million. So if you look at one of these companies, so NVIDIA, for example, okay, they're producing mobile phones for the Christmas market. 50% of their market may be at Christmas. If they miss Christmas, then they effectively have to write off a chip. So their time to market is so important. Now I know within the avionics industry, time to market's a lot longer, but the companies we're working with, the commercial pressures are getting slightly more. They're also in avionics, I think. And also in avionics, traditionally on the FPGAs, people have gone into the lab very quickly. But as the FPGA is becoming more complex, the lab time and the debug time in the lab is now becoming so long that FPGA companies or FPGA designers are starting to look for different ways of doing their verification. And we've been working with a few companies in improving their FPGA verification from a simulation point of view rather than from going into the lab too early. Okay, so that's what we'll talk about this evening. Okay, so there's a list of some of the types of verification that we would typically do in an ASIC. Okay, constrained random, which we'll talk about, functional coverage, which we'll talk about, code coverage we'll talk about, formal verification we'll talk about tonight as well. These are things which people can do. We won't talk about in detail, but these are the types of things people where you just generating metrics and analyzing metrics. So if you're using a bug tracking system, and a very basic thing is to use a bug tracking system, okay, then you can get bug rate analysis. Okay? And if your bug rate is still going up, okay, so you're running your project, okay, and from the start of the project your bug rate doing that, then you are very unlikely to ship at this date. So there's bugs and there's time, okay. If your bug rate is still doing that, you're very unlikely to ship on time. Your bug curve should be doing that, and your bug curve should be doing that, and you should be able to say, right, we're getting ready to ship. And at that point here, okay, you can start to watch those deltas. And if those deltas here are too big, you're not going to be ready to ship. So bug tracking for us not only provides us a management system, it provides us an analysis system where we can also look at, are we going to be able to ship on time? Is the bug rate coming down? If you move to constrained random, okay, constrained random bug curve, this is more of a directed test bug curve. A constrained random bug curve normally looks like that. Okay, so you tend to be able to ship earlier. But if you keep good statistics on bugs, you'll be able to do this type of analysis, which allows you to much more predict a completion date. Okay, and if you're in management, if you're either the verification manager or project manager or the commercial manager, predictability is one of the big things you're after. Okay, if your company comes to you and 1 week before, your engineers come to you 1 week before tape out and say, we're still finding too many bugs, we're not going to be able to do it. So as a commercial person, you're very annoyed. Okay, if you come here and say, we're not going to ship on time because the bug curve's not coming down, then they can maybe put some extra resources on, they can reschedule with their customers, etc., etc. So we have a saying in our company, give bad news as early as possible. Okay, always give bad news as early as possible, and then you can solve it. Okay, so bug analysis. So these aren't really advanced verification techniques, but they're very useful techniques for generating metrics. Code review completion. Have you completing your code reviews early enough Mutation analysis we'll talk about. Okay, a lot of ASIC companies just want to see a basic application running on the ASIC as well. So, for example, if you're running a chip for a mobile phone, maybe you want to see operate Android load, and maybe also you want to see maybe try and make a call on that chip. Okay, now using simulation techniques. So if you're simulating, you may get your simulator from Mentor, you may get it from Synopsys, you may get it from Cadence. It never runs fast enough to run software. So a lot of people here will map onto an emulator, which is very expensive. One of the advantages of being in the FPGA world is that you can run at speed. You can actually run software very early because you're running on FPGAs, which typically run at megahertz, which allows you to run software properly. Okay. By the way, if you have any questions, anyone have any questions? Still, we can ask a question as we go. Okay. Some of the advanced verification techniques we talk about is independent verification team, and now this is stipulated in most of the compliance standards, depending what level of safety you're verifying to. But for example, the highest level of medical software requires independent team. The highest level of avionics requires independent verification team. Independent there means separate from the developers. That could be an internal team or it could be an external company. But there has to be a level of independence, and I'll show you why. And all the requirements verified. So requirements tracking is extremely important in any compliant development. You have to demonstrate that all the requirements have been properly verified. Okay, so we were at Bosch today. Bosch is one of our customers, and we're speaking to them about how they can track from the customer requirement all the way to the test, which demonstrates that requirement has been properly implemented and is correctly implemented as well. Okay, so this is, I've been talking about this since 2001, so in ASIC this is all stuff we've been doing since 2001. Okay, so it's very mature stuff. And the question is though, which ones to adopt? Because you don't really want to say, go back to the office tomorrow and say, right, we're doing all this. Tomorrow we're going to start doing all this, because it takes too much time. Tonight hopefully you'll be able to think, well, maybe we could try that, or maybe that's an interesting one. Maybe that will give us the biggest return on investment. But these are all techniques that are very mature. It's not new. Okay, I did my first constrained random verification on a CPU back in 1996. So I've been doing constrained random a long time. Okay, so this is the first of all the thing about independence. So why do we need independence? What's the important thing what problem are we trying to fix through independent verification? Okay, so the question is, what are we trying to fix? Well, this is what happens when a designer implements code, implements a specification as RTL code, maybe on an FPGA or on an ASIC. They haven't implemented the specification. They don't implement that, they implement that. In their head, they read the specification and they make an interpretation of that specification, and then they verify it. And guess what they verified? They verified their interpretation. Okay? Now, as engineers, what you can see is there's a single point of failure in that process. And in any engineering process, you're trying to eliminate a single point of failure. So that's why we have an independent verification team, okay, that they have an independent interpretation, and they verify their interpretation against the designer's interpretation. Okay, and that's the important point here. Now, it could be that they both get that interpretation wrong, but the chances of that are very. I don't think there's any research in it, but based on experience, the chances of that are very, very slim, that they both misinterpret the specification, unless the specification is very poor. So if the specification is bad or very ambiguous, they may both take a misinterpretation. Okay, but it's what we would normally say is it's the verification engineer's job to look for ambiguity in a specification. So if a designer sees ambiguity, they may go and ask for the ambiguity to be cleared, but quite often they just interpret the ambiguity and then do the design. The verification engineer's job is to go back and say, this is, I don't know what you mean in the specification. You need to clarify the specification for me. And you go back to the requirements engineer or the architect, and you ask for clarification of that specification. You don't just verify it. You have to ask for the clarification. Okay, so that's on independence. This is on functional verification training. Okay, so I talked about some of these techniques on the slide before. These are the types of things that people are adopting. Now this is a survey that's done by Mental Graphics. It shows you the increase between 2007 and 2010. There is something on 2012. It's on our website. If you look at our website, we hold DV Club. DV Club stands for Design Verification Club. We have people speaking about design verification. On April the 8th, Harry Foster updated us on this, but we're not allowed to use that in our slides at the moment. We are allowed to use these results. Okay, and you can see here the adoption of these techniques. Okay, so assertions. Does anybody use assertions in the audience? Okay. But you're ASIC or FPGA? FPGA. But you use assertions. In System Verilog or VSL? VHDL. Okay, you use assertions from VHDL. Okay. Okay. That's a good point. I guess being an avionics audience, quite a lot of you VHDL. No, mostly. Who else is VHDL? Yeah, yeah. So that's a big difference between ASIC and FPGA or avionics. Is that avionics will tend to be more VHDL. So in Europe we see a lot of VHDL, but less so in India, in the ASIC domain. Okay, so assertions, and so what asking you a question, what's the main advantage you would see from assertions, would you say?
One of the things is to verify any particular requirement or a specification.
Okay.
Whether your code is actually doing that particular step or not.
Okay.
So in assertions we tell you yes or no.
Okay.
So that would help us to find whether we are complying to the requirements or any specific action.
Okay, so you can implement requirements of assertions to check the requirement. Okay, and you map that assertion back to that requirement. Okay, that's good. Sorry? You can debug faster. Yeah, that's a really big one. Who spends most of their time doing debug? I certainly do. Debug is the biggest problem that most people face, and there is some stats on it. It's and from this survey as well. We haven't got the slide, but debug is about 35% of our time on any project. At least 35% is on debug. Assertions help with debug as well. The reason they do that is if you're trying to find a bug in your code, I always think there's two things happen. One is the difference in time. So if you have a bug, okay, and when you're doing verification, you find a bug. You don't find the bug, you find the implication of the bug. So your test fails because of this bug, but it doesn't fail immediately. It can fail 1 cycle later, 10 cycles later, 100 cycles later, maybe 1,000 cycles later. And if you look at that time gap there will have a big factor on how easy it is to debug. Okay? And then if you look at your code space, okay, the thing that detects the bug or the failure, remember you detect the failure and you have to analyze it to find the bug. So the failure point in time, but also the failure point in the code. Okay, so if you've got a big code base and you've got a big code base here. Okay, so that's just a representation of the code, and your bug is there, but it fails over there, and you've got a big gap as well. And if you run in simulation time, and the bug is here, but your test doesn't fail to up there, you've got a big gap in time as well. Assertions, because the assertion is normally near the bug, and it fires very quickly. So using assertions, it normally fires very quickly, and it's very close to it in space as well. So if you're doing debug, I always think about time and space, because I want my failure to be close to my bug, both in time and in the code. So assertions tend to close those two gaps. That's why they're really good for debug. Constrained random as well. We'll talk about constrained random simulation on the next slide. code coverage. Did we do code coverage? I think code coverage is probably mandated, yeah? For certain safety levels, you'd probably get code coverage is mandated. Maybe statement, sometimes branch, MCDC as well. So you get MCDC mandated for you. You have to do that. And functional coverage as well we'll talk about. So this is an interesting one as well in terms of formal verification, adoption of formal. We'll talk a little bit about formal. Okay? So, this is what the mechanics of an advanced test bench. This is what an advanced test bench looks like. So we've got our DUT. That may be the whole design. It may be a block within the design. So sometimes you can do the whole design in one go, or you break it down into different blocks. The thing you have to concern ourselves about, and it's maybe a bit low, this says active, this says passive. So for me they're orange, I think on here they're a bit browny orange, and the light green. Active and passive. These are active and passive elements of the test bench. And so this will become clear as we go through. Okay? So these are active elements of the test bench. This is a driver, and this is the thing that's responsible for wiggling the pins. Okay? So your I/O is driving the pins on the design. Okay? Now the reason we have a driver here, okay, because at this level is a level of abstraction. So let's imagine you've got an interface on your design, maybe an I2C interface. People are comfortable with I2C. So this is maybe an I2C interface here. What you want to do is send in packets. So at this stage here, you're sending I2C packets, and this driver says to send that packet in, I know what the protocol is. So it turn your I2C packet into the appropriate protocol signal wiggles here. Okay? So at this end, you're now working at the level of transaction rather than at the level of pins. Okay? So straight away, you've moved the level of abstraction from pins to transactions. And that's a very important step in advanced verification. You have to move from pins to transactions. Okay? And that's our stimulus generator. Okay? And these are active because this is generating packets and this is driving the duct. And they're doing things. They're driving the duct. So we call them active elements. Okay? And then during your stimulus generation, you can constrain the information in those packets. So imagine it's an I2C packet going to a particular address. Then you may want to constrain the address and the data. But you randomize those, but you don't want them to be completely random because this may only have a certain address space. So you say random addresses, but only within the allowed address space. So you then, what you're doing is constraining your address space to only the valid part of the address space. Okay? Also, when you're trying to do coverage, it may be that you then constrain even further and say, right, there's a particular register I'm trying to hit, or a particular block of registers I'm trying to hit, so I'll now constrain even further to just hit those registers. So you use the constraints, first of all, to get to the legal space, and then get into the corner case space. Okay? So you use constraints in two different ways. And maybe also here, I think I2C can do, is it 7-bit and 10-bit? I can't remember precisely. So maybe you want a 7-bit address or a 10-bit address, and then you can constrain the length as well. And the data, sometimes data is important, sometimes data is not important. And then you write your test in terms of those packets. So you might then say, right, I want to send in loads and loads of packets to these addresses, and then read them all back. Okay? But now your test writer is dealing with transactions rather than signals. So you've raised the level of abstraction. Now, a UVM environment is a lot more complex than that. So that's the simple version of a constrained random test bench. That's a very simplified version of a constrained random test bench. Okay? And you can see the active parts there, driving our duct. They're all active. Okay? Can you read this? It says monitor. Okay? So now you can see the first passive element here. It's monitoring what's going on the duct, but it's only doing I/O. Only black box. What it's doing is looking at the I/O. Okay? So it sees what's going into the duct and it sees what's coming out of that. Okay, and it's passive because it's not affecting the duct at all. All it's doing is watching what the duct's doing. It watches what goes in, watches what comes out. Okay, and what? Oh, sorry. There is sometimes a need to do internal. So this is what's an internal signal. So that takes you from black box to white box. And white box verification is usually harder to maintain because if the internals of the duct, at this point here, we don't care what happens inside the duct. As long as the pins don't change, our test bench doesn't change. Our test bench is stable as long as the pins are stable. As soon as you do this, and you track internal signals, you then become dependent on the internal state of the design. So if the designer changes the hierarchy, the designer changes the signal name, and you're tracking that signal name, and your test bench breaks. So you have to be very careful with white box. That's why black box, we always try to do black box. Sometimes you have to do white box. Okay? And then these are transactions. So this monitor sees this, turns it back into transactions, and passes those transactions to a checker. Okay? That checker will then be modeling the duct, and if it sees something goes in, it expects something to come out. So what happens is the monitor says, I've just seen this packet go in, okay, pass it to the checker, and the checker says, right, that packet's gone in, I now expect this packet to come out. And the monitor says, I've just seen this packet come out, pass it to the checker, and the checker then says, was that the packet I expected? Was that the transaction I expected? Okay, so now what you can hopefully see is there's no human involved in this at the moment. The human's written the test bench, and the human's written the test. So once the human's written the test, everything just goes without any intervention. There's no intervention anymore. Okay, and assertions as well. So you can pass these monitors to assertions. So these assertions may be embedded, and maybe that's what you do in the VHDL. You embed it in the design. So you can put the assertions directly into the VHDL or into the Verilog, or you can have it hanging off the monitors. Okay, and quite often these will be doing protocol checks. It's just obeying the protocol. Okay, and you pass it to functional coverage as well. Very bright colours, but you pass it to functional coverage. Okay, and that all gets into a coverage database as well as code coverage. So there's three types of coverage going on here. Okay, functional coverage, code coverage, and assertion coverage as well. The coverage, assertions, I don't know if they do it in VHDL, but if you write assertions in System Verilog, they automatically give you coverage as well. Then, so for example, if you're normally an assertion says, if this happens, then I expect this to happen, and it will give you what we call an antecedent of a consequence. So if A, then B. Okay, that's a typical structure of an assertion. If A happens, then I expect B to happen. And what assertion coverage does is to say, did A actually happen at any point in that simulation? Because if it doesn't happen, then your assertion passes vacuous, so what we call vacuously. Because there is this is the trigger, there is no trigger event, therefore this is a vacuous passing of your assertion. Assertion coverage would say, actually A never happened, so that assertion is useless. So assertion coverage is useful to say, did I actually have the trigger event on my assertion? Did my assertion fire? Okay, and you've got code coverage as well, and you've got functional coverage. Okay, now what? So if you look at why, at the moment, that is a test bench that can just run by itself, and because this is constrained random, effectively you've got random data constrained in some way. Every test you run will be slightly different. Every single test you run will be slightly different as long as it's got a different seed. So in the random environment, each test will have a seed which is maybe a 64-bit number. So the chances of repetition are tiny. Okay? So there's going to be no repetition, and you just keep running these tests, and it will run a different test every time. Okay? And you can run 100 in parallel, we work with ARM. ARM in Cambridge have 2 buildings full of machines running simulations. All those machines that run simulations, there must be a couple of thousand machines running simulation after simulation after simulation. Same test bench just keeps running. Okay. Yeah? Proper. Yeah.
That generated proper outputs are not how we confirm it. We confirm the driver. Right?
But how do you mean by proper?
Proper inputs are given or not to the driver.
To the driver?
Yeah.
Because, well, proper from what perspective? It's a well-formed packet.
Yeah.
So the driver normally doesn't accept, if it doesn't, well, there's a compilation perspective, but also when the driver receives the packet, it unbundles it and turns it into signal, pin signal. So if it can't unpack it, normally the environment won't work, or it won't compile or something like that. So, but you've got a good point, is how do we know this test bench is doing what we expect? Okay. Well, yeah, sometimes also you deliberately put an error in this packet. So when this packet arrives here, it gets rejected because you need to do error checking as well. Okay? So sometimes you deliberately put an error in here, and the driver will pass that error on. So for example, if you're passing data that's got some sort of ECC check on it, and you put a bug in the ECC calculation, then this should reject that data. But you want to test that, so sometimes you deliberately inject bugs in this. But when you develop this environment, that's when you check it and you try and check it all. So it's the test bench. Yeah, there may be a bug in the test bench, and quite often there are bugs in the test bench. I think on ASICs now, there's normally more code in the test bench than there is in the duct. So by definition, you're probably going to get more bugs in this than you are in this. Okay? So there will be bugs in the test bench. You have to just try and fix them. Yeah. But yeah. Yeah.
Suppose we write a basic test bench.
Yeah.
Then you take the credit of the test bench also has to be validated.
Yeah. Yeah.
So how do you do that?
Well, how do you do it on your VHDL test bench at the moment?
So we are right now we are generating a stimulus.
Right?
We are generating a stimulus.
Yeah.
So here we have normally we have not started the DO254 process.
Yeah.
We still not done the test bench.
Right.
If you wanted to know how what validation of the test bench happens, then when we are getting our actual report, we will just simple
the validation of the data, I'm not sure in terms of what you mean.
test bench validation. In my framework,
Yeah.
I am developing an IT code.
Yes.
And I have written a test bench, test bench for that.
Yeah.
Now I want to validate whatever test bench I have written to take the credit out of it, so that I can take a direct credit instead of randomly generating.
What do you mean by direct credit? I'm not sure what you mean by direct credit.
No, credit means in DO254 process.
Yeah.
I simply just cannot take whatever the data out. I have to follow a process.
Yes. Yes.
I have to follow the entire code coverage. I have to with the entire CDC is working or not.
Yes. Yes.
Yeah, right. So here I just wanted to know how this statement helps to take the credit of the test.
Okay. So there's on that. So we'll come back to that. So if by the end the slides haven't answered your question, we can come back to it. But I think the slide answers what you're trying to say. And for those, I just realised it's not easy to read it, but this says checker, this says assertions, this says monitored. I think this is, there may be a colour missing on this one. Okay. But if you, I think the slides will answer your question, and if not, we can come back to it. Okay. So this is now generating, and it's automatically checking. So you've got an automatic checker in place. So you can leave this running, and it will just generate tests and check those tests, generate tests, check tests. But what you don't know is what the test bench has done. You don't know what it's actually done, and that's when you put in the coverage. That will tell you what you've actually done inside the test bench. And this may be new to you, functional coverage. So we'll just give some examples of functional coverage now. Okay. So what is functional coverage? So here's some examples. Okay, the system may transfer packets of different sizes, and the following size or range of sizes may be observed. So if you've done some boundary value analysis, maybe you've done some boundary or equivalent partitioning or boundary value analysis, and you think I want a size of 1, 2, 3, 4 to 127, 1 to 252, 253, 254, 255. What you can actually do is take those, we call these buckets, and then here, as this monitors, okay, it passes to the functional coverage, and the functional coverage will say, have I seen all of these values? 1, 2, 3, any value in the 4 to 127, any value in 1, 2, 8, 6, 2, 5, 2, any and one of these values. And it will look for those values. So it will tell you at the end to say, you've now generated all of these packet sizes. Okay? So that's now told you that you've done what your test plan said you needed to do. Your test plan is saying, write all these packet sizes. So within a VHDL test bench, you probably write a test for each packet size. And you write those tests and off you go. In this environment, what you do is you let it run, and this tells you here whether you've actually covered those sizes. Okay? So, and that's why you get this curve. Okay? Because in directed, you start finding bugs straight away. In constrained random, you take a long time to build the test bench, but then all of a sudden it goes woof. It goes really fast, and it starts hitting all these coverage points for you. So rather than doing one by one, they get done automatically for you. But you have to invest the initial time to build the test bench. Okay? And then you can do cross coverage. So you may have said, actually, what I want to do is see these sizes going to particular addresses. So I want to see. So if you've got, you get a classic matrix. So maybe you said sizes 1, 2, 3, 4 to 127, etc. And maybe going to addresses 0, address H. Address AA, address FF, some addresses. I'm not sure what the important addresses are. Okay, and then you can then say, right, what I want is that, and I want those as well. I want 0 to all of these, but AA is only going to be important at the top and the bottom. And you can create these matrices by what we would call cross coverage. Okay. Or an example here for CPU, where an ALU has done all of its supported operations with different input pairs of registers. So if you're doing a CPU and you've got maybe 4 or 5 registers which the ALU can operate on, has the ALU done all of its operations on all of those registers. So quickly you can build up these coverage models very quickly, and then your automatic test bench will try and hit that functional coverage for you. Okay, and so what you can do is try and close coverage. Your coverage graph, again, in directed, if you're looking for coverage, so this is coverage rather than bugs. In a directed environment, you tend to proceed like that, okay? Because you're doing directed, and you know, people work at a certain rate. In advanced, you tend to do that, and there's a lot of research shows that this is earlier than that. So these okay. So what we've worked with people before, and they find this a very hard thing to do. It's a big step for them. Some constrained random is a big step. But what you can do is take your current test bench. So this may be your VHDL test bench, and it's directed. Okay, and these are the active parts. Remember, this is the active color. You're not throwing anything away. You're still using your existing test bench, and you can start to put in maybe some checkers, okay, assertions inside, and functional coverage as well, okay, and code coverage. So you don't have to go all in one go. Some people move slowly towards this. Because this test bench is hard. This is a big test bench. It's a big move to build a test bench like this. So some people do it in steps. They keep their current test bench and just add in some. And this is why it's important to distinguish active from passive. Because all you're doing is adding, probably that should be green as well, sorry. Because that's passive as well. That's not active, that's passive. But it's shown in red because it goes inside the code. You're actually changing your code base a bit. Okay? But you've done an added passive element. What you're trying to do is add value to your current test bench. Okay? So, here's some of the techniques. And I've tried, this is my personal analysis of how you can add those techniques. Code coverage. So I think probably most people are doing code coverage already. If you're in a DO254 environment or a compliance environment, you'll already be doing code coverage, probably up to MCDC. Functional coverage you're probably not doing. It's reasonably high effort, but it allows you to check that all the major functions are fully verified. Okay, so when somebody writes a directed test, you can check that that directed test is doing what you expect it to for a functional coverage model. So if somebody comes back and says, right, I've now written I've got my test bench and I've written to all these addresses. Okay, normally you may go in and do a code review to make sure the test bench is really doing that, but you could also do it by functional coverage, by looking at the functional coverage point and generating the functional coverage to make sure that person has implemented those tests correctly. So you could add in functional coverage here just to check that the tests are doing what you think those tests are doing, and that's quite. You can do that without disrupting your current test bench. Assertions. That's what varies the number of assertions, but high value. I think you've seen two people already who use assertions and say they're very good, and they can be added straight away. If you look at this, assertions can go straight in, either straight into the code or hanging off some sort of monitor. You can put assertions very high value very, very quickly. So that may be the thing you think. If I was going to go and impress my boss tomorrow by saying I've learned something which I think we can do within our environment, the assertions are probably the cheapest one and the one with the quickest ROI. And the checkers, these checkers here can be quite complex to write. They're written at a high level of abstraction. They need to be written at a high level of abstraction. Some people write them in C, so you can do a reasonably quick model of an I2C. So the I2C is written in VHDL or Verilog, and your checker is written in C. It's a very high abstract model. It just says if the transaction goes in, what do I expect to get out? If I write to an address and then read back from that address, and they expect the same data to come out. Those checkers are very quick to write, and it may be that you can improve the checking on your existing test bench, because if you're writing directed test benches, you have to predict what the expected outcome is. There's a lot of mental activity goes into predicting what the expected output is. And also, what happens a lot if you're doing directed tests, you check what you expect to happen. You don't check that what you don't expect to happen didn't happen. So there's a double negative in there. But normally when you write a directed test, you say, I'm writing this directed test and I expect this to happen, and I'll check that it happened. But normally you should also check that nothing else happens. And that's the bit that most people don't do, because it can be a lot of checking to make sure. You've got to think of all the things that could have happened that shouldn't have happened, and you have to check that none of them happened. Checkers quite often just do that automatically for you. So you can have a lot of value just from writing a checker as well. But the assertion is the biggest, the quickest thing. Constrained random is high effort, very high value there. If you get it right, it's very high value. And that's why the ASIC industry do it, because the cost of a bug is so high. And a lot of adoption of advanced verification techniques depends on how much does a bug cost me, how painful is the bug, okay? And as the pain of bugs becomes higher, you start to adopt more and more advanced verification techniques. and the pain of bug in ASIC is very high, and I think it's getting higher in DO254. So we've got all this, and we've got a nice advanced verification testing. But one of the things you have to remember, okay, is what do you have to do to find the bug? What do you have to do to find the bug? So first of all, no matter how advanced your verification test bench is, it's all zeros and ones. Okay, you're doing unless you're doing an analog, and I think we're probably most people digital here. Any analog people? So we're all digital. That's good. So you're feeding in ones and zeros, and you're getting ones and zeros out. Okay, what we're doing is in the advanced verification, we're trying to raise that a level of abstraction so that you can easily write tests. You don't have to write tests in terms of ones and zeros. Nobody wants to write tests in terms of ones and zeros, but that's what's going into the dart, and that's what you're getting out of the dart. So you have to get the right sequence of ones and zeros to find the bug. Okay, so the bug's going to be there, and you get the right sequence of ones and zeros to hit the bug. Okay, and now what you've done is stimulate the bug. Okay, but if there's no checkers, imagine you wrote a test bench with no checkers, you'd never find a bug. Okay, you could be the best test bench in the world, it could be the best stimulus in the world, and it could get 100% MCDC. You've got no checkers in there, you're never going to find the bug, because you've got no way of detecting it. You have to detect failures, and that bug has to propagate to what we would call an observation point. Observation points are typically outputs, because we typically monitor outputs, but you can monitor, you can do white box and monitor internal signals, but typically it's black box. Typically you're looking at outputs, and you're monitoring it, and you're watching it. There's an eye there, but the last thing you want to do is do anything manual. Okay, I know people still look at waveforms, and that's a way of detecting a bug. If your bug works its way to a signal that's in your waveform, and your person who's watching it sees it, then that's an observation. Okay, but typically what you want to do is automate that observation. Okay, so you have to have all these three in place. You have to have all these three in place. You have to stimulate the bug. The bug has to propagate itself to an observation point, and then you have to observe that what you actually got out was not what you expected to get out, and you get a comparison failure. So that's how you find bugs. Okay, you stimulate the bug, it creates a fault or a difference, and you detect that difference from what you expect. Okay? Even if you're doing manual, even if you're looking at waveforms, that's the process you follow. Okay? And what we're all good at, and we're all very good at, is this bit, the stimulation, because we can measure it. If we don't get 100% MCDC, we know there's something wrong with our stimulation. Okay? How do you measure how good the checkers are? Okay? And this has been a problem for a long time. How do you measure the checkers? How do you know you've got enough checkers? How do you know you're doing enough checking? It's virtually impossible to know you've done enough checking. And the one thing that does it now is something called mutation analysis. Okay? And again, it's a quite expensive technique. What it will do is at the end of your verification process, and you say, this verification engineer said, right, we've done it. Okay, we're confident. We've got 100% MCDC. We've done all the stimulus, all our requirements are tested. We've done all the tracking. We've validated our test bench. We think everything's done. Okay, we're signing this verification off. This design is ready to go into the airplane. Okay, what this does is it takes the design and it injects bugs deliberately into the design, and it runs your tests to find out if it finds all those bugs. Now, if you inject 100 bugs and you only find 80 of them, then your verification wasn't good enough. If you inject 100 bugs and you find all 100 bugs, your confidence can be pretty good. Okay, so all it's doing is saying, I finished my verification, I'm done. Okay, we'll take a copy of the design, deliberately inject bugs, and see any of the bugs you find. Okay, and it's automated now. You can do that manually. You can do that manually. And I always think it's a good thing that at the end of a verification, you go back to the designer and you say, right, I think I'm done. The designer says, right, I know your corner cases. what I'll do is I'll change a greater than to greater than or equal to, or maybe I'll take a signal out of sensitivity list, and then rerun your test and tell me if you find tell me whether you find those bugs or not. Okay, you can do that manually, but a lot of it's done automatically. Okay, and I always think that's a really good test of your test bench. We call it testing. You sort of verifying the verification. Or validating the verification. Can our verification find all the bugs? Okay. Okay. So now we've got this one at the bottom, but it can be quite high effort to adopt a tool. I know some of this may be hard to read. We can send the slides after. I think Shyam will send the slides to you afterwards. But you can do it yourself. It's low cost if you do it yourself. Okay, you can just ask your designer to stick some bugs in and see if you find them. This relies really also on your test bench being automated. Okay, because if it sticks 100 bugs in and you have to manually run all your tests 100 times to find it, it's going to take you weeks, a very long time. So this really does rely on you having an automated test bench. Okay. So some other verification techniques which people use, advanced verification techniques people use. So the FPGA here. So we found, and maybe PCIe is not the right one, but on FPGAs that we work with, we're starting to find what we would call hardened IP. So some of you, do any of you use FPGAs with an ARM on them? ARM processor? Yeah, so some of you may be using, and it's hardened. Okay, you don't map the ARM onto the FPGA. The FPGA comes with an ARM embedded in it, and it's already in silicon. That ARM is already in the silicon. Okay, we call it hardened IP, or it's embedded IP. Okay, and it's also coming now with some more interfaces. So one of the companies we were working with had a PCIe interface. That's probably not particularly avionics oriented, but maybe there's some interfaces that you may have on there. Maybe I can't remember now. But so the company we were working with went into the lab. Here's their design. That's their design, and that's the hardened IP. And so that's the interface to get data into their design. And they would go into the lab. And that's nice and easy. You go into the lab, you connect up the PCIe, and you can start pumping data in. Okay? And you can maybe run some tests, you can write some tests. It becomes very hard to debug. And you don't know if you've got all the PCIe protocol covered. So what we did with them, using the simulation environment, we said to them, well, why are you verifying that? You don't need to verify that. That's given to you. So this is called verification IP. I'm trying to remember now, it's an Altera FPGA, and there's an internal bus on the Altera FPGA. I can't remember the internal buses now. But you can generate transactions onto that internal bus as if they come through the PCIe. Okay? So you can then verify the design directly without having to go through the PCIe, because this is what you want to verify. To a certain extent, you trust it because it's delivered by the customer, and maybe it's customized off the shelf. You can get you can push it through a COTS flow. So you want to get straight to your design, okay? And so as I think as more and more we get hardened IP, especially on the interfaces, you'll see more of this. We did in the end also do some PCIe traffic as well, because what they're also concerned about is are they connected correctly to the PCIe. So they wanted to verify this interface as well. And that doesn't verify the interface to the PCIe. It's generating traffic directly into their logic. Okay, so they're trying to verify their logic, and they can stimulate the logic directly without having to go through this, because this is delivered. But at the end, they did also just want to make sure that the transactions, and then they went into the lab, and they found that the lab work went much, much more quickly than before. And so PCIe is probably not a protocol you use, but you may find that over time you're starting to see more and more hardened IP onto the FPGAs. I know, for example, what is that for Avionics, the ARM? It's encryption related. Okay. Yeah. Okay. Okay. So, as to the rise of design IP, we've seen the rise of verification IP as well. So the ASIC industry now, there's a big market in verification IP. So if you went to your vendor tomorrow, maybe it's Mentor, maybe it's Cadence, maybe it's Synopsys, Aldec, do people use Aldec? Yeah, so Aldec is quite popular in FPGA and Avionics. But I think still Mentor dominate. How many people are Mentor? Yeah, but this is a simulator rather than... Oh, Xilinx have their own simulator, of course, yes, yeah. So you may be using a Xilinx simulator.
You've got everything in the software.
Yeah.
Yeah.
They've got the whole tool chain, haven't they, Xilinx? Is the simulator faster? Yeah. So I've never had... I think the VGA vendors simulators are usually better than the Xilinx simulator. But yeah, you can do everything within the Xilinx tool chain. And Altera as well, have their own tool chain. So, Micro 7, they got bought, yeah, they got bought, yeah. But you're right, so you can use the Xilinx one as well. Does Xilinx support System Verilog now? Yeah. It supports System Verilog, Xilinx?
I don't know,
Okay, yeah. So, so I guess people are using the FPGA vendor tool chain as well. Yeah. Does anyone use Mentor graphics? No. Right? Yeah. Okay. So the Xilinx simulator. Synopsys, people use Synopsys? So Synopsys is on in Cadence? Yeah. I guess Xilinx as well. So in the ASIC world, you'd find mostly Mentor, Synopsys and Cadence. I think as you move into Avionics and FPGAs, you get the Xilinx tool chain, you get the Aldec tool chain as well. But I don't think there's any others. No. Okay, so you've looked at functional verification approaches, and we've been on this side of the graph so far. So static is where you don't execute the code. You don't always have to execute the code. Okay, and we're going to see some techniques now where you don't execute the code. That's called static versus dynamic. And we've been looking mostly at from a dynamic simulation point of view. Have you got the time? Have the time on? 7:40. Okay. So we'll probably go to 8 o'clock and then the lunch is okay? Okay. So we're going to start looking more now on the static side. So we've looked at simulation. Static is where you don't execute the code. And you can do that by review. Okay, you can just do code reviews. Code reviews are a very good way of finding bugs. You've got static analysis tools as well. Static analysis tools like linters get used very, very heavily in software, less so in hardware. They get used a lot in software static analysis tools. And we're going to talk about formal now. Formal verification. So formal verification is being adopted more and more widely, certainly within the ASIC world, where designs are becoming more and more complex, and it's very hard to find the bugs by simulation because the space, the design space is just too big, the verification space is too big. So we do a lot of work with ARM. We help ARM on CPU verification strategy. So we spent a long time in ARM helping with their CPU verification strategy and how they do it and how they verify their CPU. And during that time, we were there about a year. We spent about 200 days with them in a year helping with their verification strategy. During that year, a bug came in from it was an ARM 7. They estimated that ARM 7 CPU had been in the market for about 7 or 8 years and was in at least 1 billion phones. Okay, so 7 years in 1 billion phones, 7 billion years of use on that CPU, and then someone found a bug. Okay, so if you think of how many simulation cycles that CPU had been through on those phones, there's no way And ARM just recognizes there's no way they can find all their bugs with simulation anymore, because there's too many corner cases. They can't hit all the corner cases. They can't even identify all the corner cases, let alone try to hit them. So normally they try and get all the corner cases, they put it into a functional coverage model, and then they've got their 2 buildings running 1,000 simulations, and they try and hit the coverage model. Okay, but they realise now that's virtually impossible. So they start to use formal verification as well. A lot of people start to use more and more formal verification, and this is where you try to prove properties about the design. You don't run the design; you try and prove properties about the design. So here's the property. 2 signals are never asserted on the same cycle, so mutually exclusive. Okay, and you try and prove that about the design. I have to be very, very quick on this because we're running out of time. The way it works, if you think of the simulation space here, so you start at reset, where all the register values are known. So everything's in a known state. So you've got a single state because everything's known. And on the first cycle, after a certain number of inputs, certain flip-flops can take, or registers can take different values. So you start to get different potential values on those states. And by the time you've got up to maybe 10 cycles, there's more potential states than there are stars in the universe. It gets too big too quickly. What our simulation does is this. Okay? What you're effectively doing in a simulation is finding one way through that state space. Okay? And one way through that state space. Okay? And if this already has got more stars than, more states than stars in the galaxy, the chances of you getting hitting bugs is quite low. Okay? So simulation is what we call depth first. So if you ever remember computer science when you're talking about search algorithms, that's a depth first search algorithm. What formal does is on cycle 1, it will check every single possible state on cycle 1 and look to see if these 2 signals are asserted or not. And then on cycle 2, it will look for every single possible state and see if they're mutually exclusive. And it does that. And through the power of mathematics, there's a lot of proof engines to try and prove that actually on every single possible state, those are always going to be mutually exclusive. So it does, the formal we're doing what we call breadth first. Okay? And if one thing you want to remember about formal is when somebody asks you, well, why is formal different to simulation? You can always say, well, the simulation is depth first search and formal is breadth first search. And if you keep that picture in your head, it's always a good way of remembering the difference between dynamic and static. Okay, so there's some other example properties here. These are types of things that you may want to prove about your design. Okay, they're useful properties about your design. You can write them as assertions, and you can run them in simulation, but you're only doing a depth first search because you're running in simulation. You're not proving them, which you'll get from a formal tool. Okay. As you say, you can check them in simulation. This is one which you can never check in simulation. It's called a liveness property, and it says a stall can never remain high indefinitely. So there may be a stall signal, which is maybe stalling a pipeline on the CPU or stalling data going into a FIFO. And you're running a simulation, and that stall goes high at that point. Okay? Now your simulation, by definition, is finite. So at some point you stop your simulation and the stall's still high. But what you don't know is that if you run it for 4 more cycles, the stall is going to go low. Okay? And you can never know from simulation this type of thing because it's talking about infinite time. But formal understands infinite time. Formal can do proofs about infinite time because it's a mathematical technique rather than a simulation technique. So this type of thing can only ever be done in formal. Okay? Formal takes 3 inputs to the tool: the model, which is usually RTL, a set of properties, and there's some properties there, and a set of assumptions. So it's similar to what I said in in the simulation environment, we have to constrain to be legal. You also have to constrain this, but only consider the legal space. Okay, so some of these are going to be illegal, and you have to constrain them away. Okay, so there's some examples there. Usually RTL, maybe Verilog, maybe the HDL. Items transmitted to one of the 3 destinations within 2 cycles of being accepted. So I requested the bus, I got the bus, and within 1 or 2 cycles it got to one of its destinations, A, B or C, received it. Okay. That's a system Verilog assertion. I don't worry too much about the syntax, but hopefully you can see that's quite a powerful thing to say. If I make a request and I get a grant, then within 1 or 2 cycles, that packet has to be received at one of these 3 destinations. Okay? And if you can prove that, it's a very, very powerful thing to prove about your design. And here's the constraint. It says that if I make a request, but I don't get a grant, then I must keep my request high. Okay? And that's a very succinct way of saying that constraint. So there's some protocol to observe. If I make a request and I don't get it granted, I must keep making my request. I can't just put my request up and down, up and down, up and down. If I put it up, it stays up until I get a grant on the bus. Okay, and that's the constraint there. And what will happen is you say that got proved. I've proved that property. It's a fantastic result. I've now got a proven property. It failed. Failed could be one of 2 things. Either you found a bug because the design doesn't satisfy the property which you're trying to prove, or you're under constrained, okay, and you found a bug here in the illegal space rather than the legal space. And the other thing it does, and this is the big drawback on formal, so again one of the things you can always remember from tonight, a big drawback of formal is that what happens here, because this state space is exploding, as I say, down every single cycle, the state space is getting bigger, 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 bigger. The formal tools can run out of memory and fail to do the proof. And it can say, I got to cycle 10 and I didn't find a failure, but I couldn't prove it either. I haven't proved it yet. And it will just say, I've explored it for 10 cycles, but I haven't proved it. And this is a difficulty, is that this one is a sort of undecisive result. You don't know what it means. Really. You have to interpret that result. So I'll skip this because we're going to run out of time otherwise. But formal is very, very powerful. Just remember the fact that as well as proving, it can be useful to find bugs, but not always you get results. Sometimes it's non-deterministic. It doesn't know if it can't prove it, but it can't find a failure either. And what I'll do is send you these slides so you can look through these afterwards. But there's some strengths and weaknesses with formal. But this is really strong. The fact you can just stress the design and find a lot of corner cases, which is very good in ASIC, not so good for a compliance point of view, because it's very hard to measure what you've done there. If you get a proof, then that's a very good point for compliance because you've actually got a result. Okay, but in compliance, if you get this, it doesn't mean anything. So from a compliance point of view, it's very hard to say what you've done. Okay, and the potential issues are limits on the size of the design you can do. If you get explore, then you don't know what it means, and it's non-uniform runtime. The good thing about simulation, if you look at these simulations on our depth first search, normally they all run for about the same amount of time. You can predict how long your simulation is going to run, and normally I know these simulations are going to take 5 minutes, and I know over 24 hours, therefore we can run 1,000 simulations, and we know what we're going to do. And what can happen here is formal can take a minute here, then 5 minutes, then 10 minutes, and this may take 2 days, 3 days, 4 days, 5 days. So it's unpredictable, and managers never lack unpredictability. Okay, so talking about safety critical systems now, so we're going to, those techniques we've talked about, we're going to see now how we can try and fit those into a compliance environment. Okay, So these techniques, maybe advanced, maybe they're nice to use. It's leading edge, but somehow you've got to deliver compliance. You've got to demonstrate to the authority that you've done a proper verification, and you've verified all the requirements. So how can this fit into the compliance system? There's some examples. We're focusing on DO254 for hardware. We do a lot of work as well in DO178 on the software side of Avionics. We do a lot of work in ISO 26262, which is more about automotive. We do a lot of work in ASIC 62304, which is about medical device software. And all of these are actually very similar. They're all very similar to each other. They talk about process objectives and outputs. They don't really normally say how you must do things. They talk about the processes you must follow and the outputs you must generate. So they don't tell you how to write your test bench. They don't tell you have to write directed tests or constrained random. But what they say is you must have processes with objectives, and you must create certain outputs which allow you to demonstrate, to go to the authorities with an audit trail. So, for example, there's some of the documents or outputs which DO254 identifies that you must produce as part of your process. So hopefully you'll recognize most or all of those as things, as hardware verification engineers in the DO254 arena, the types of things you need to be producing. Okay? And what we're going to focus on is these two, because these are the ones where the advanced verification can help. It can help you on a verification plan, but that verification plan is only good if you've got traceability data as well. So, we're going to look at how the last 10-15 minutes, how can advanced verification techniques help with the hardware verification plan, and also to demonstrate that from a traceability point of view, you've actually verified those requirements. Okay. So a closer look, the hardware verification plan describes the procedures, methods, and standards to be applied, the processes and the activities we conducted for the verification of the hardware item traceability data, establishes a correlation between the requirements, detailed design implementation, and verification data to support configuration control, modification, and verification of the hardware item. Again, it's not prescriptive. It doesn't say you must do your verification in this way. It tells you what you must produce from your verification to demonstrate to the authority that you've done your verification properly, and it satisfies the standard. Okay, so we're looking at those two. So here's the requirement sheet. This is something we use in ISO 26262, which is automotive, very similar to traceability data in DO254 as well. You have a set of requirements, some safety requirements as well. You derive safety requirements as well. You derive an intent to implement. Then you've got a verification and test plan with that's your intent to verify, and then you've got proof of implementation for your test results. So that's how we organise in ISO 26262, and we do similar in 254. And this tends to be a bidirectional tree. So it's much better if you've got a bidirectional tree, so you don't just trace it one way, you can trace it back as well. Okay, so you say, well, if I'm missing this proof of implementation, what requirements get affected by it? You can do impact analysis downwards, you can do impact analysis upwards as well, because you want to be able to do impact analysis. Okay, and that's what we, in our ISO 26262 work and our DO254 work, is we break down the requirements. Hopefully you can see here, this is typical. You're breaking requirements down to smaller requirements or features maybe, and you're breaking those down maybe within your requirements analysis tools. So doors, most people doors users. Doors, yeah. So doors is a big one. Avionics. So maybe you've got this hierarchy within doors, okay, and so you've done your requirements tree within doors. Then what we would do is map that onto our verification goals. So typically, if you're using directed test benches, this may be a directed test. You say, I'm going to write a directed test or 2 directed tests to verify this requirement. And I'm now going to, and so what you've now got is you're mapping these down onto directed tests. So that doesn't work with advanced verification techniques because you haven't got directed tests. You've got random tests. And you measure the effectiveness of your random tests by your functional coverage or your assertions. So what we would do is map these down maybe to a functional coverage point, or an assertion, or a proof, or within your constrained random. Remember I said that the randomness is all controlled by seed. And it's important that you have the seed because you need repeatability. Okay? So your constrained random environment, although it looks random, it's actually randomized purely by one seed number, which is fed to the test bench. And if you give the same seed number, the test bench will do exactly the same thing. So it's called maybe pseudo-random because it's all constrained by this seed. And that seed is randomly generated. So if you feed the same seed to your random test bench, it does exactly the same thing. So sometimes in here, you can map it to a test, directed test, because as soon as you're giving the same seed, you're getting the same test. So you can actually map to what we would call directed tests, and directed means the same seed does the same thing every time. Okay? And so all we're doing here is different goals. So what you need to be able to do is map your requirements to different verification goals rather than just traditional directed tests. And we can map these also to code coverage. So you may be mapping it to MCDC. So you may, on a particular unit, want 100% MCDC to sign off that requirement. Okay, so you can map it to structural coverages as well as functional coverage, as well as assertions, as well as formal proof, as well as directed tests. Okay. So here's an example. This is SPI actually rather than R². See that there's similar things. What we would do in our hardware, and this is for an ASIC, I think, where we said, right, for this SPI master, we've broken it down to reads and writes on the bus with a 10-bit address, 7-bit address, 10-bit address. There are verification goals. These are the sub-features. Okay. And we can also do stuff in software. Maybe we also want to verify a software driver working with that. Okay. So we've broken this SPI master, which is the requirement, down into its sub-features and how we're going to write the test. But what are the implications for the requirement sign-off? Okay, as I said before, you can't just map now to directed tests. We have to map to functional coverage, code coverage, assertions, formal proof. Okay, so lots of different ways that we need to now be able to sign off our requirements, because our requirements method and our verification traceability is still important to us. And what we have to do is, if we want to validate our verification, we have to demonstrate that every single requirement has been properly verified. Okay. And we need to automate pass-fail, coverage collection. Okay. And it all needs to be linked to configuration management data as well. You have to know what version of the design you give this verification on. Okay. So you have to make sure that the configuration management, configuration data management is done properly as well. Okay. So, this is a very, very high-level view of what we're doing. There's our EDA tool. Okay, that could be the Xilinx tool. This is the simulator, effectively. So it's either the Xilinx tool, it could be a Mentor tool. I know some people use a Mentor, maybe Cadence, maybe Synopsys. Okay, when that runs, it generates a database of coverage information about what it did during that simulation. So for each simulation, you get a small database telling you what that simulation did. There's now an industry standard called the UCIS API, which allows us to read out of that database. So this is our test bench. So the test bench I showed you earlier is running in simulation under that EDA tool. The EDA tool is generating, remember we talked about code coverage, if you're looking at MCDC, the MCDC data is in there. Okay? And when the simulation runs, it generates a database with all that coverage information in. Now if you're doing functional coverage, the functional coverage information will be in there as well. If you're doing code coverage, the code coverage will be in there. The assertion coverage will be in there. It's all hidden in that database. And each EDA vendor tends to have a different type of database. But some of them that are standardized on this API. I'm not sure Xilinx have, but Cadence have, Mentor have, and Synopsys have a slightly different API. And also some of the formal tools have done as well. So some of the formal, if you want to do mathematical proofs, they're also right to the database. What you want to be able to do is unlock that database and match it up to your test plan. For us to be able to do requirements sign off. So our requirements now of our tree, that's mapped down to our test plan. So maybe the requirements are held indoors. Okay. I know some people try and put their test plan indoors as well. Our experience of doing this is that it's quite difficult. And not how many people do the test plan inside doors as well? Okay. Is it hard or is it easy? It's easy, okay.
The only problem is to exactly link to the code.
Okay.
Exact code. Exactly do that particular test plan.
Okay. Okay. So what about updating that test plan? How do you get the results in there?
Yes, it is like manual.
Ah, okay. Yeah. So this is the difficult bit. The test plan, then you have to get the manual. So if you're writing directed tests and you're saying you're manually saying that pass, that pass, that pass, that pass. Okay. If you move to advanced verification, that becomes really hard because you have to go through this database and find all the functional coverage points. So that becomes a hard thing to do. And this is really hard to do as well. Maybe you could use DXL, but I wouldn't advise it. So, okay. So that's where quite often when we work with customers it breaks. Some other people put the test plan into, we were say at Bosch today, they put their test plan into QT, I think.
Actually, Bosch is the store, but they have integration with
quality. HP Quality Center. HP Quality Center. Yeah. So I think what, for example, Bosch do is they have doors here, and then the test plan, they export the requirements tree into Quality Center. They put the test plan in Quality Center, but it's still a manual update. They still update manually. Okay. So what we do is we use this. This is our tool, Shoreshine, which automatically extracts all the data from here. And so within the requirements, the extraction from doors, we create the test plan here, and automatically then the data from this simulation is automatically mapped to that test plan. Let's think of so here's, what it does also is it looks across time. Okay. So this is a history of the regressions, okay, and the data that we got from those regressions in terms of how much of the requirements have been properly verified through time. Okay. So going back to this is so the difficulty with using these advanced verification techniques, I think as the gentleman said, what you can do is take your requirements here, and you can map it maybe to requirement. So you break down the requirements, okay, and your test plan here. So this is the requirements tree, and then in your test plan, you say I'm going to write directed test 1, directed test 2 here, directed test 1, and directed test 2 here, okay, and then you run those tests over in your simulator. Okay, maybe it's Xilinx simulator, and then you look at the results of those. You run those 4 tests here, directed test 1 to 4. You get the results of those directed tests 1 to 4, and then you manually write them back here. Yeah. Okay. Okay. And that's, I think, it's fairly typical for DO254, which people do at the moment. Okay. The problem with that for advanced techniques is that you're not running directed tests. You're running continuous simulations big simulations which are generating functional coverage. This generation is looking at assertions. Maybe you're doing some proofs inside a formal tool. Okay, so the data here is very different to the data you get from a directed testing environment. And what you have to do, be able to do, is be able to take that information out of this database and map it back to your test plan. And that's a difficult step. But it is possible. It is possible. So you can map, rather than map your requirement to a directed test, you can map your requirement to a functional coverage point and then make sure that functional coverage point has been hit. But you do need to be able to read that functional coverage point from that UCIS API or out of this database. Okay. Yeah. Sorry? Yeah.
Both have a requirement tools, like
yes. Yeah, so Mentor have a vector.
So they also provide a centralized database
yes.
for connecting to this. And for mentor tools, you have Quest Approach, which
yes.
gives you all the verification,
yes.
and which feeds back to your requirement. So
yes.
upward, downward, forward,
yes.
capabilities are there. Yes. So what I want to know, what is that?
Our tool is very similar. So what the gentleman says is very correct. So within Mentor, Requisite Pro, I think it's called, it uses a tool called Rectify. So there's a requirements tool called Rectify, made by Dassault Systems, which are a big avionics company, and they use that as the requirements analysis tree. Okay, and then they have a verification planner where you can map your requirements onto functional coverage, code coverage. So they do this, and it exists within Mentor. I'm not so sure about the LDEC one. I haven't used the LDEC one, but I've used the Mentor one. Sure. Yeah. So that enables you to do advanced verification techniques within Mentor, within LDEC. And what we do is we do the same. But what we've done is saying that our tool does very similar to Mentor. I could go into details of what's different, but basically it's the same, apart from the fact that we don't care who did the simulation. With Mentor, he's dependent on Mentor. Yeah. Yeah, they're tools only. So you're locked into Mentor, you're locked into LDEC. So with ours, but what your question is a good one, because what it demonstrates is that the industry knows how to do this. The industry knows how to map requirements onto advanced verification goals. Okay, so the goals you're mapping onto on your test plan are advanced verification goals, coverage, assertions, code coverage, formal proofs. And so we know how to do it. And Mentor have got a tool to do it, LDEC have got a tool to do it. What we do is our tool, the simulator could be anybody, because this UCIS API is supported through Cadence, is supported through Mentor. I think LDEC support it. Synopsys don't. I don't think Xilinx do. And so one day you could be running. One day this could be Mentor, the next day it could be Cadence, and we don't care. And what a lot of the ASIC companies try and do, they try to avoid lock-in to a particular company. Because as soon as you're locked into Mentor, your price might go up a bit. So, as soon as you're locked into LDEC, then your negotiation power diminishes quite a bit. Okay. And what it doesn't do is as you say, is to hook into other requirement tools. Because what you don't want to do, and a lot of companies have got big investment involved. They don't want to throw that away and say, okay, you've got to start again. So what you want to be able to do is interact with your chosen requirements tool. And none of these tools are as good as DAWs. The DAWs is a very good requirements analysis tool.
We like a system requirement.
Yeah.
So it's a reliable requirement.
Yeah.
Now they have small modules of FPGA. Those requirements get transferred to your rectified to our tools.
Yeah. Okay.
And then they can change follow and after traceability also change.
Okay, so you're still doing your requirements within DAWs and then transferring it to Mentor and transferring it back. And that's what we do as well. And I think so don't go away thinking you're the only one to do this. Mentor do it as well, and Aldec do it. And I think the fact that 3 of us can do it demonstrates that these techniques can be used in compliance. And then it's a matter of choosing the best vendor. So we do, I've got more experience on that on software than hardware. And a lot of the software tools would allow you to do on-target coverage analysis, for example. But on the on-target, very difficult to, these techniques really only apply in simulation. So it's very difficult to do that on-target.
Are you able to do it at speed, or you do it reduced?
So this is most of Aldec, Mentor, and us will all do via simulation, which is simulation speed rather than at speed. Okay. So there are ways of doing functional coverage on FPGA, and you can do it at speed there. So most of these techniques will only apply in simulation and not apply at speed. So there is a problem there. There's definitely a problem if you're trying to do all your verification at speed. Is it so? Yeah.
Using a level application.
Yeah.
Okay. Then I use this methodology.
Yeah.
With your tool.
Yeah.
Then what will be the consequences? Because I will not get it at speed. Then what is the solution for it?
Well, what do you want to do at speed?
Suppose I want to develop a framework,
yeah.
Like using your tool. I want to use those. I want to use your active signing. Then I want to test at speed results I want to get. So that 100% coverage I get.
Right.
Right. So what is the method? How do you do it?
So how do you measure the coverage?
It directly provides on at speed CVT compiler.
Okay.
At speed. It goes into a test vector,
okay.
comes into at speed, it reaches a sense point, and pull back the data.
Okay. The coverage data.
Okay.
So we wouldn't be able to do that. We can do some. There are some at speed vendors which can give us the data back, but we'd have to work with those vendors to pull the data back into here. Yeah. For us, no. But Aldec sounds fun. Yeah.
With that solution, you cannot keep this process. Even though you cannot say ultimately the only test I want to see is on the chip.
Yeah.
If you really think about it, then your development time will be more because you want to reduce the number of errors in your code itself. So you better do this one. Then you get some errors, solve this, then get into that.
I think it's the decision as to how much you do in simulation, how much you do at speed. Yeah. 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 And also, but do you have to do at speed? Or? But yeah, it's a good question. Any more questions? So I think hopefully I've taken you through some of the advanced verification techniques. These techniques you've been using a long time. These are not new techniques. They've existed a long time. I've been doing constrained random nearly for 20 years now. It's a very mature technique. And I think what will drive or push the DO254 industry into this is the complexity of the design. If at some point you just can't, the complexity is too high, you can't do it directly anymore, you can't do it at speed, all that speed anymore, then you'll be pushed into this into more and more advanced verification techniques. The good news is that you can still do this. You can still sign off a compliant design using these techniques, and the tools exist, Mentor exists, Aldec exists, and they exist as well. But hopefully what you've learned tonight is a bit about some of the advanced verification techniques, how they work. Some of them take a lot of investment, some of them take less investment. assertions take certainly less investment. And you can adopt those, but you still have to map the requirements to verification results and goals. Yes, sure.
Same thing when you're using this your
Yeah.
model.
Yeah.
Now, what you have to find for observability implies that the source should be available part of the project. That means what tool you are developing and what results you are giving.
Yeah.
It should be traceable from requirements.
Yes.
So you have a certification kit for this kind of thing.
Yes. Yeah. You have that certification kit. Yeah, you need that as part of the certification. Yeah.
And what is the way of applying it? Like, do I need to buy the entire source code certificate, or it's on your side directly? Suppose sir government wants to see your source code. So if we are buying the entire source code, or sir already goes to your place and says,
Well, for the certification process, I have to try and remember because it's different for different industries. But we do medical, we do medical and avionics and automotive. So I can't remember. Do you know what Gaurav is behind you? Do you remember what the qualification process for avionics is? Yeah. So an independent agency would come in and vote, and for some compliance you have to do it per project.
No, why I'm telling
On
you,
some,
we have already undergone the project.
Okay.
That we bought some compilers from US.
Okay.
Okay, the source code of the kernel was not available with us. So our search authority in India went to US, went into the company, they kept the entire details, they verified.
Okay.
Now, actually, even at A, for testing tools, source code is not to be verified.
Yeah.
If it's automated output, there is a testing tool.
It's a testing tool. Yeah, it doesn't affect your. This is. Yeah, I understand the question. Yeah. So that's a good answer. Yeah, because it's only a testing tool. It's not affecting your source code at all. So for your compiler. Because it's not required for typically for verification tools who are not doing anything in your source code. But it has to be qualified. You have a qualification process, and the reason I get confused is because some industries say you can qualify the tool, and then it can be used on different projects. And some industries say you have to qualify the tool for the project it's being used on. And avionics is that way, is it? Yeah. So avionics, yeah. So you have to qualify. But you get a qualification pack. So the vendor gives you a qualification pack, which allows you to qualify for the project. But you don't have to go through the source code because it's not, as the gentleman says here, it's not doing a compilation. It's effectively black box. Okay. Any more questions? So hopefully you found it useful. And some insights into some advanced verification techniques. I think there's some food, so the buffet is open, so go and enjoy some buffet, some drinks, and if you want to talk some more, we're here to talk. So Gaurav maybe should identify himself. Do you want to stand up, Gaurav? Because Gaurav looks after Sure Science, he's our development manager. So maybe I can see Gangadhar as well, and more. Do you understand? A few T&VS people maybe just want to stand up. So if you want to know some more, you can. Okay. So if you want to ask them questions, they'll be in lunch as well. Okay, thank you very much for coming. Hope you enjoyed it, and hope you found it useful as well. Okay, thank you.